I guess I can just jump in and start to tell you about what's an inverse problem. So, which will be the general setting of this talk. So if you just go on Wikipedia and look at the definition, you will find that an inverse problem in science is the process of calculating from a set of observations the causal factors that produce them. So if we put that on a little sketch, we can think of the problem this way. We have some input that is unknown, and we can think of it as a vector in R to the n or C to the n. And then it's transformed by a process that we know more or less well. So here I know the function f, and I have some little n that stands for noise. And it produces some causes or observations y that can be thought of as another vector of a dimension m. And this is what we have access to. And now the forward problem would be to go from x to y. And the inverse problem is from y, recover x. It's nice because my notations are quite on par with, for example, the tutorial of Bob yesterday, where we also had the observations that were y. So people will be hopefully following more easily. And this general process is, of course, something that as scientists we do, I guess, almost every day. And sometimes there are situations where we can expect for a perfect recovery. Actually, this channel that transforms the inputs in the outputs is something that is somehow invertible. But there are many cases in which we have some loss of information, and we are still trying to know what to find out what we can know about the inputs. And of course, this is a problem that, as I was saying, is very, very general, and we are not going to cover how to solve inverse problems in general today. What we are going to be focused on is how we can use some prior knowledge on the inputs in order to help the reconstruction. And we will follow two main axes, one being the sparsity, and the other one being neural network priors. Before we dive into those topics, let me maybe tell you about examples of simple inverse problems, and one being classes of those being linear inverse problems. For linear inverse problems, we are thinking of problems that can be written in this fashion, where we have the function f that was general before that can be reduced to a linear operator that we can write as a matrix A. And although this seems pretty restrictive, actually there are many problems that can be modeled in this way in real life. And there can be also substantial challenges in solving it. So to give you a few ideas, of course, there can be signal to noise ratio issues. So you may have a noise of too high amplitudes, which prevents you from recovering information about the input. Then the linear system you have to solve might be overdetermined, underdetermined, and following that, it may be non-invertible, or you can have a matrix that is badly conditioned. All of this be making it difficult to solve this inverse problem. And to give you now concrete examples of instances of this linear inverse problem, I can think, for example, of an example in genomics, where we will have y that is a vector that stands for patients being either sick or healthy. Then the matrix A will have as its rows the genome of all of those patients. And then we are trying to recover a vector X that will be indicating which are the losses that have some relevance in predicting the sickness of the patient. So that's one possible example. Another example, this time in image processing being one of the main focus actually of this tutorial, is deblurring. And in which case A is a convolutional operator. So for example, with a Gaussian kernel. And you have, for example, an input image just like the one that is up there, X, that will produce some observations that corresponds to a blurred image, so convoluted with the Gaussian kernel, more or less blurred given of according to the variance of the kernel. And you want to recover from the blurred image the one that is unblurred. And that amounts to solving such a linear inverse problem. So, okay, of course, so there are many situations that can be actually modeled as linear problems, but there are also situations that are intrinsically nonlinear, and in which case we cannot really say something a priori about the form of the problem. I mean, it will depend on what you are interested in. And it can be as diverse as a PDE solution or a quadratic system or whatever you would like. And then, of course, there are also many challenges in solving these problems. So related to the one we mentioned before, there is the problem of well-posedness. Does the solution exist? Is it unique? Is it well behaved with respect to when we change a bit the inputs? Thinking a bit ahead of how we are going to solve this problem, we may have some convexity issues in the optimization to find a solution, and so on. Again, to give you a few examples of famous nonlinear inverse problems. In seismology, we can think of the inverse problem of trying to understand what is the density profile of the ground beneath our feet as a function thanks to the recuperation of some waves that are reflected. So we are perturbing at the surface, which is sending a wave in the underground. And then we are collecting all the reflections of the waves. And the reflection of the waves will tell us about the discontinuities in the density underneath the feet, our feet, and so enable us to find out all the different layers. So that's one famous nonlinear inverse problem. And then one, again, in imaging, and that is arising in many, many different situations in astronomy or in coherent diffraction imaging, is phase retrieval, in which case we have X, that is a specimen of interest we are trying to image. And then A will be the Fourier operator, so transforming X in his Fourier transform. And then we will only have access to the magnitude of this Fourier transform, potentially noisy. Okay, so that's a few examples of inverse problems. Now, how can we use some prior knowledge on the signal in order to help the reconstruction? And the first type of help we are going to get is from sparsity. So it turns out that many of the signals we are interested in admit a sparse representation with respect to a certain basis. So sometimes it's easy to find the basis in which the signal is sparse, just because it's the natural basis in which we are thinking of the problem. So for example, in the genomics example I was giving, we expect that only a few locations in the genome will actually be relevant. And so we expect that this vector X will actually be sparse directly. Or if we are thinking of the interfaces in the ground, we don't expect to have so many different layers. So we are also looking for an outcome which is sparse. But sometimes we need to work to get the right basis, or we can resort to some standard basis in which we know that signals are often sparse. So that can be the Fourier basis, or for images, the orthonormal wavelet basis that is particularly interesting for this kind of problems in imaging. And if you haven't heard about orthonormal wavelets, the way they work is that you have a mother wavelet, so a mother function, such as this one. And then you consider the family of functions that is generated by translating and scaling the function. And that will give you this psi of L, the scaling factor, and M, the translational factor. And then if you decompose, for example, this brain image among these bases of orthonormal wavelets, you get something like this, where you have different pictures that correspond to different scalings, rotations, and you have among the picture the different possible translations. And what you can see is that those decompositions are mostly gray, meaning that they are mostly zero. And that's indeed the representation of an image in the wavelet basis is sparse. Okay, so how do we now use this sparsity information in the inverse problem at hand? If we start by focusing on linear inverse problems, we are going to try to solve the following sparse regression, where we have a data affinity term, so something that makes our forward model A of X fit the observations Y. And then we have a constraint on the sparsity of the signal that is here written as the L0 norm, which is directly counting the non-zero coefficient of a vector, and that we constrain to have to be lower or equal to some assumed level of sparsity. And if we think about this, for example, in the very simple problem of denoising an image, here we will have, so the linear inverse problem being Y, the observation of the noisy image, and then A, the matrix that allows us to go to the orthonormal basis, and then X being the sparse representation of the image, plus some noise. And the algorithm can be pretty easy. We can, so this was the original data that I was showing you on the slide before. Now we have noisy observation image. We can decompose it in the wavelets basis, in which case we will see that the decomposition is not sparse anymore. Yet what we can do is only keep the k wavelets that have the largest coefficients in the decomposition. So that will be only keeping, for example, the ones that you see here in black and white. And then we construct the image from this decomposition of wavelets. And you can see that using only a small number of wavelets, we are able to denoise an image very easily, implementing this idea. Nevertheless, in general, this sparse regression I was mentioning is an NP-hard problem, because the algorithm I was just showing you is something that relies on the fact that the wavelets are an orthonormal basis, and that is not something that we will have access to in general. And so there is no efficient polynomial time algorithm to solve this sparse regression in general. So as a result, it's a very active area of research in signal processing, and there are many different types of algorithms to try to solve this sparse regression. So I'm definitely not an expert on all of them, but I can just mention a few. So greedy algorithms will try to find serially what are the components in the sparse representation that contribute the most to the observation and discover them one after the other. There are Bayesian methods, which are something that we heard about by Bob yesterday morning, that are going to try to model some prior information about the system, and also incorporate a model for the stochasticity of the observations. And then there are convex relaxations methods, which are pretty handy and that have a nice intuition behind, and that I will try to tell you a bit now about. And before I can do so, I will need to make a parenthesis about LP norms. So that's something that I guess most of you know, but it's just a quick reminder that if I write the norm P of a vector, I will have, so the definition being the sum over the components of the entry to the P, and then taking the P as root. And the examples that we are maybe used to manipulating are the one with the low integer P's. So the zero norm is counting the number of non-zeros. The L1 norm is summing the modulus of the entries, and then the L2 norm I don't even present anymore. And now if we think about the geometry of those norms, so here I'm plotting the balls of radius 1 in those different norms. We have all those different sets for P is equal to 0, 1/2, 1, 3/2, and 2. And they have interesting properties, being that for P strictly smaller than 1, the sets that we are defining are concave sets. And otherwise, they are convex sets. And then you can also notice that for P strictly smaller than 1, well, smaller or equal to 1, sorry, they are spiky. And otherwise, they are not spiky. So why does this matter to us? Well, if we think about this sparse regression I was telling you about, and if we think of it as a constraint optimization problem where we are going to look at intersections of sets. So if we are constraining the L1 norm, we are going to constrain something in this box for a certain level K of sparsity. If we constrain the L2 norm, we are going to constrain something in this disk. And now if we had the sets of signals that will be reproducing the observations. So here, since it's a linear regression, we will have such sets where here we have the sets that ensures that this fidelity term is smaller or equal than a margin epsilon. And you can see that in the case where we are using the spiky sets, the L1 constraints, the solution will be on one of the axes, which means that the solution will be sparse because it will have some components being 0. So you can see how using these spiky sets is helping the sparsity of the solution. But also it's much easier to use this L1 constraint than an L0 constraint, because the set that we are going to have to optimize over is a set that is convex. So this gave birth to very famous algorithms that were discovered in different communities simultaneously. So it's called lasso in the statistics community and basis pursuit in the signal processing community. And it's basically solving this regression problem under the L1 constraint. And under structural assumptions on A, actually, this problem returns the same results as the problem constrained with the L0 norm. It's still harder than solving something with the L2 constraint because the L1 norm is non-differentiable, but it's easier than with the L0 norm. And if we, I think somebody is not muted. It's, please, yeah. So if, so it's easier than the L0, and it's still a very active research area to find some efficient algorithms for solving this problem. But if you are interested in, you can just go to one of the famous distribution for machine learning, scikit-learn, and you will have a comment that will implement this model for you. Are there some questions up to here? Okay.
Yes. Doesn't this reduce to linear programming, basically? The linear programming with constraints, like the simplex method?
Maybe. I'm sorry, I'm not familiar with this.
Okay.
But I'm sure somebody in the audience will know if. And okay, and so all this I mean, success and interest for solving inverse problems based on sparsity actually triggered what I could call the complementary idea of compressive sensing. So compressive sensing was proposed in the early 2000s, and the idea is that if signals admit sparse representations, they are compressible, and then we should be able to design acquisition methods that would directly acquire the signal in a compressed representation. So the implementation of that will involve some sub-Nyquist sampling, meaning that the number of measurements we are going to take is not proportional to the size of the signal and the level of the resolution we want for the signal, but is related directly to the level of sparsity of the signal. And this can be done directly by rewriting this little in linear problem I was writing, where we are assuming here that we are in the basis in which the signal X is sparse. And we are going to collect a vector Y that will have a dimension M that is much smaller than the dimensionality of the signal through the multiplication with a matrix A that will be therefore short and wide. So it will have much longer rows than columns. And of course, now the question and the reconstruction will be using the same ideas as before for the sparse regression. But we need to put some efforts to design a measurement matrix, which is this matrix A, that will provide an efficient reconstruction, because it's not, of course, not possible for all of them. And there are a lot of theoretical works to give guarantees for the minimal number of measurements M as a function of the level of sparsity and the different properties of the matrix A. But without entering those details, I think the important idea is that randomness is particularly efficient. And for example, you could take A being a Gaussian matrix with random IID entries, or randomly subsample Fourier, and be very efficient in this compressive sensing. So compressive sensing now has had a lot of impact, and everywhere where measurements are either expensive or time consuming. And so I took this figure from this recent review about compressive sensing, and you can see, according to what you are most interested in, that there are many areas of applications now of compressive sensing. Maybe one of them being the most famous being medical imaging with accelerated MRI, that hopefully I will quickly hint out at the end of this tutorial. Okay, so what we have seen is that exploiting sparsity could really help in solving those inverse problems. And although we focused on linear inverse problems, the intuition carries over to nonlinear inverse problems, and there it's harder to give some general algorithms. It would really depend on what's going on in the problem that you are looking at, but there are definitely some help that can be taken from this idea of exploiting sparsity. So those are, I would say nowadays, classical methods and classical ideas. And if you're interested in starting with those topics and those algorithms, I wanted to recommend the nice reference of those two websites by Gabriel Perret, who are, especially the numerical tours of data science, is providing some notebooks in every language that you would be interested in, probably, in R, in Julia, in Python, in MATLAB, with examples of those little algorithms, and that are very nice. Okay, so now what we are going to see is how we can use more sophisticated models of signals, which are neural network priors, and how we can use them in inverse problems. So before I start that, maybe I can also, it's a good time to ask questions if there are more. Okay, so let's dive into the neural network priors.
Marylou, sorry, can I ask a question just to follow up on your the lasso issue?
Mm-hmm.
It looked like if people look at the chat, by the way, then Aaron's question did get answered. So it looks like linear programming can be used to solve lasso. But from my remembering how Christian and his collaborators did it, is lasso usually solved iteratively? I don't know if you were going to say much about solution methods.
No, I mean, I'm not in the. So I think there are many different ways of solving lasso, and I'm not an expert. For example, indeed, I think. I mean, I feel intimidated by the fact that Stefan Mala is talking afterwards, and I'm sure you could tell us much more about this literature.
If I could, this is Anirvan, I'm just making a comment. So there were two bounds. One is the L1 under K, and the other one was like Y minus AX norm less than epsilon. If you do it component by component rather than the norm, then clearly that can be made into an LP problem, right? With slack variables for each. But if you say the whole norm is under, it's better to do this Y minus AX square plus lambda AX1, and that's a quadratic programming problem. If you write each X as difference of two non-negative variables, right? And then this L1 norm can be written as so in general, some convex optimization problem, not always LP, can be used for that. It could be a quadratic programming in some problem versions. And also there are many methods. One of them is that you can just crank up lambda or change lambda and track solutions. That there are zillions of different approaches which are iterative. Yeah, it's a whole industry of.
Okay,
yeah.
thank you.
Yeah, maybe something I didn't say, which was on my slide, is that indeed we can also rewrite the problem as a Lagrangian formulation with the language multiplier to incorporate the constraint on the norm.
Yeah.
I'd make a comment on that too. You know, there's yet another, the whole industry of this, as someone said, but there's also a thing called elastic regularization as well, which just combines L1 and L2. And that one has sort of nice properties for both. It makes it kind of smooth because of the L2, but then as it approaches the 0 point, it then vectors over to one of the coordinates and makes all the others 0. So it starts out very convex, and then only at the last moment kind of switches over to driving things to 0. And then of course you can just change Lagrange multipliers to drive it one way or the other.
Yes. So yes, I mean, it's there are a lot of methods and still like ongoing research topic as yeah. So
Cool.
okay.
Thank you. Sorry.
So now let's jump to I mean the second part of this tutorial, which is on neural network priors. And something that I will have to tell you about along this tutorial is generative models, which are how we are using the expressivity of neural network to model the data distributions that we are interested in. So there are different architectures that we can use to do this that will go along different sampling methods. And there are different ways of training those so-called generative models so that they can grasp the statistics of the data sets that we are interested in. So I will walk you through those different architectures as well as telling you how we can use them in the inverse problems. And the first class of generative models that I want to tell you about are restricted Boltzmann machines, which are historically the first type of neural networks, of generative models, and that are energy-based models, meaning that they're actually an undirected neural network made of 2 layers, an input and an hidden representation, which units that are typically binary 0, 1, and then that defines joint distribution over the 2 layers, that it takes the form of a Boltzmann measure with an energy function that will involve some terms that are pairwise between the inputs and the hiddens, the inputs and the hiddens, so in this fashion. So if you are a physicist, this should remind you a lot of an Ising model with some local fields and couplings, which in machine learning are called biases and weights. And but then the difference with maybe the Ising model from statistical physics is that here we are going to define the probability over the inputs, so the space in which we are interested, by marginalizing over the hidden variables. And doing so, we are effectively allowing interactions at all orders between the different coordinates of the inputs. So we are not restricted to those pairwise terms of our interaction. We can effectively model any type of correlations between the pixels, if you want, of the pictures. If, for example, if X was to represent an image, and this makes it a class of a very expressive class for probability distributions. And then to train such a restricted Boltzmann machine, we will do so in supervised learning, meaning that we will have a data set of examples. So for example, here we have MNIST, that is a data set of unwritten digits. And we are going to maximize the likelihood of this data set. So we are going to maximize the probabilities that the model is assigning to seeing this data set and maximize over the parameters that are the weights and the biases. And that will give us so a set of parameters theta that will be the train parameters that we can use afterwards to sample the restricted Boltzmann machine. So this will require some Markov chain sampling. And I mean, this can be done successively one layer to the next. And then hopefully we'll get samples that resembles the one that we had in the training sets if our training was successful. So we learned a representation of the data that is incorporated in those parameters. So the applications of those restricted Boltzmann machines, historically, they were used to pre-train deep neural networks. So now it's not the case anymore, but that was one of their primary usage, where each layer was pre-trained as a restricted Boltzmann machine unsupervisedly before having the full learning of the deep neural networks on a supervised task. And they are also very popular, actually, in the physics literature that is starting to use neural networks to help different areas of physics. So for example, in biophysics, RBMs can be used to model some neuronal spikes. They can also be used to study protein sequences. And of course, they can also be used in quantum physics to represent density functions of many body systems. And that was a very important paper by Giuseppe Carleo and Matthias Streuer that I think was also mentioned yesterday. So and now how can we use those restricted Boltzmann machine to solve an inverse problem? Well, we can look at this, go back to the example of the compressed sensing. So recall that we have Y that is a vector of observations that corresponds to the multiplication of X with a measurement matrix A. And we have very few observations compared to the size of the signal, but which is assumed sparse. And here A you can think of it as being a Gaussian IID. Then if we want to exploit prior information to get X from observations Y, if we have access to typical samples, for example, we can compute the expected sparsity. So for the MNIST dataset, it's 150. And then with the observations and one CS algorithm, so this is, we used here approximate message passing, which is an algorithm that I didn't mention, but is one of the many that you can use to solve compressed sensing. And then we can look at how the sparse prior is helping the reconstruction as we are increasing the number of observations that we are taking, so the number of measurements. And although the expected sparsity is 150 and the dimensionality is 784, we can see that with 100 measurements, so less than the sparsity, we start to have something that looks like a 6, apparently, in this observation that we took. But what we realized during my PhD in the group I was working with in Paris is that if we have access to typical signals, we could also just train a restricted Boltzmann machine to represent the data distribution of such type of images, and then plug it in the reconstruction. So we had an algorithm for that. And then see how this is helping the reconstruction. So first, we used a binary RBM, which is only modeling the locations of the non-zero pixels in the image. And then we used a full RBM that was also modeling the value of the pixels. And we can see that in this first version, with maybe 80 observations, we start to have something that really looks like nice 6. But when we have a full training of RBM also on the values of the pixels in the image, then with as little as 60 observations, we are able to do the reconstruction. So of course, the RBM has learned the spatial correlations between the pixels, and so it greatly improves the reconstruction. And this triggered the phrase of whether neural networks were the new sparsity. And this may be surprising, but of course it's not, in the sense that we worked more. We had to have access to a training data set, which is something that is, of course, more information than just knowing the expected sparsity, and then train the neural network to get to those level of improvements. But it's a very nice idea that we are able to combine those two to improve the reconstructions. So that was with restricted Boltzmann machines. And as I was telling you, this is something that is very, historically important and still very popular in the physics community. Also because they yield some results that are maybe more interpretable than other types of generative models. But in the machine learning community, they kind of fell out of fashion. And this is because deep generative models were invented, which is another class of generative models. So, and maybe before I move on to this, were there some questions about the first example with restricted Boltzmann machine and compressed sensing? Okay.
Marylou, I'll ask something. So the digits that come out in your work here, the 6, mm-hmm. This is one sample from the prior. Is that from the RBM distribution?
So
you happen to have sort of chosen the same sample each time, so that it always came out as 6.
Oh, sorry, then it wasn't clear. So what happened is that I gave this 6, so a 6 that was from the MNIST as an X. Then I measured it with a matrix A. And then I only had access to the observations Y. And I was wondering whether or not I could recover the 6 from the mere knowledge of a vector Y. Okay. That had different dimensions. So the smaller the Y, the harder the problem.
Oh, so you're only observing 60 pixels or something?
I mean, it's 60 Gaussian projections.
Gaussian projections, okay.
Yes.
Like Retina would or something, yes. Okay.
And cool. So we are seeing how many of those Gaussian projections we need in order to reconstruct the signal. And this is greatly improved by the addition of a trained RBM in the reconstruction process.
All right, thank you.
Welcome.
I have a quick question. It seems that if you go from 20 to 40 to 60 observations, while the sparse prior sort of doesn't look great for any of them, and the 6 begins to emerge out of what clearly is not yet a very good solution, the RBM seems to be completely wrong and then suddenly right. Is there a way to quantify the robustness of that? So, I mean, is there, I mean, in the sense that even for 20 or 40 observations, the RBM seems to really decide on some form rather than give you a diffuse cloud. And so I was wondering, in terms of quantifying the uncertainty of these restrictions and realizing at what point the reconstruction is believable, in what sense?
I understand your question. So, so with this method of approximate message passing, actually, we are effectively estimating entire posteriors. So we have access to a variance of the estimate that we are producing. And I confess that we didn't check it, but it would be interesting to see if the variance of the estimate is indeed becoming much smaller when it's getting towards the actual solution of the problem. That's an excellent question. But I mean, it's here we are touching upon two interesting things, I think. First, the fact that as humans, we have a prior of thinking that, oh, this is just undecided, whereas this is decided, but this is wrong. But this is kind of our representation of the fact that the blur is undecided, but it's still, it's the output of the reconstruction. But it would fool us as being, this one would fool us as being something that is a true minimum, if you want. Whereas this one, we would just say, oh, okay, the algorithm doesn't know. So I think that's interesting. And then the other thing is that indeed the neural net was trained on a distribution. So it's trying to project this distribution in everything he's going to see. And that we'll see later on in the tutorial how the problems that can come from this kind of approach and one element of solution towards this.
Marylou, I have a follow-up question. A little bit like on intuition, why adding the RBM makes it better?
So it makes it better because if you want, when you are doing the reconstruction, you are taking into account the correlations that are between the pixels of the signal, because those were learned by the RBM, and it learned how images of handwritten digits are having correlations between the pixels and what they are. So this is why it's helping a lot.
Thanks.
Okay. So now, next generation, if you want, deep generative models. So what are deep generative models? They are modeling distributions in the following way. So they have an input layer that is a simple latent distribution. So you can think of P of Z as a multivariate Gaussian, for example. And then you have a feed-forward network, the kind of neural network that is just a highly non-trivial parameterized function that creates the output X that we will be interested in. So that is just a function g theta of Z, theta being the parameters of the neural networks that can be learned. So how are those deep generative models trained? Well, it's the same story. So you start with the data set to do your unsupervised learning. And there are two main paradigms. One being to maximize the log likelihood or equivalently minimize the KL divergence between the empirical data distribution and the distribution defined by the model. And again, this is maximizing here the log of the probability of observing the data sets given the model. And this is, for example, the paradigm that is used in variational autoencoders that we heard of yesterday from Ashley. And there is another paradigm that has brought some great improvements and that is quite different, which is called adversarial training. And that is for generative adversarial networks. And in the adversarial training loss, there is some additional element, which is an adversary that is a discriminator. And the discriminator is another function, another neural network that is meant to distinguish between samples that are drawn from the data distribution, so from the training sets, and samples that are actually coming from the generative models. So it works in the following way, the loss. So you are computing the expected log of the probabilities that the discriminator is recognizing a genuine sample as genuine, plus the expected probability log of the probabilities that the discriminator is recognizing fake sample as fake. And then you are trying to make the discriminator as good as possible. So you are maximizing that with respect to the parameters of the discriminator. And then you are minimizing that with respect to the parameters of the generator, meaning that the generator is trying to generate samples that are as good as possible so as to fool the discriminator. That the discriminator is not able to make the difference between what's real and what's actually generated by the model. So the key point about those deep generative models is that they can include convolutions. And in this way, they were the first generative models to be able to generate very convincing images, for example, of faces, sorry. And in this case, of course, they don't have the little Tory architectures that I draw up there, but they look more like this deep convolutional GAN, where you have many different channels and different filters for convolutions and many different layers. But eventually what those architectures are able to produce is, for example, those pictures of faces of people that do not exist. And why are they such good, interesting representations of the data? So that's the intuition is that they are effectively, they are capturing the effective degrees of freedom of the data sets that we are interested in. So if you think about the images of faces, so images live in a very high dimensional space, but maybe that the space that is occupied by images of faces is a much lower dimensional manifold in this large ambient space. And so here you would have different faces traveling in this manifold, whereas if you would go off the manifold, what you would see is just random noise. And now thanks to the architecture of the generative model that has a small latent distribution, this is exactly what is being learned in a way, this low dimensional embedding of the class of images, for example, we are interested in. And we can verify that by doing interpolation in the latent space. So here we take 4 different samples of a generator that was trained on images that are related by the fact that they share some of the coordinates in the latent distribution. So, I mean, those 2 will share one, those 2 will share another one, and so on. And then we can look at all the images that we would generate if we are just changing those, I mean, we are interpolated between the different value of the latent coordinates. And you can see that you are able to actually generate images that always look like faces and that continuously go from one image to the next. And so you are really just having those latent coordinates that is capturing, if you want, the variability of your network. And so we have this intuition now that if we have a good low-dimensional representation of our data, we should be able to exploit that in inverse problems. And so we can go back to this compressed sensing problem that I was telling you about. So I mean, I'm just putting back the little sketch where we have y that will be a vector of observations we will have access to, and we will try to go back to the x that generated those observations, knowing that y is much smaller than x. And the way to do so with the generator is to find an image in the range of the generator that is in accordance with the observations. So ultimately, what we are going to try to do is to solve the inverse problem with having something that produces with the forward model something that is close to the observations. But now we are going to optimize over the value of the latent representation Z. And interestingly, this optimization can actually be done quite straightforwardly with gradient descent algorithms. And if we look at the number of observation, I mean, the reconstruction error as a function of the number of measurements, we compare this with the solutions that would correspond to looking at the sparse basis of the images, so either the Fourier base or the wavelets, and then apply the lasso, we can see that we have much smaller reconstruction error as a function, I mean, as with much fewer number of measurements. And this can be also seen by looking directly at the reconstructed images, where on the top row, you have the original image. And here you have the 2 solutions using the lasso and the sparse basis. And as a last row, you have the DC GAN solution. For here, a number of measurements that is 2,500 compared to I mean, images that live in much bigger dimension. Okay, so this was an example, but we can phrase it much more generally. This strategy to use inverse problems to, I mean, to use deep generative models to solve inverse problems. Sorry. So we are going to change this original problem of finding x that minimizes this difference.
Can I ask a question on the last slide? How do you so what you're trying to do is find the set of inputs that generate something you desire, right? I mean, if you have an original image, you'd like the generator to be producing that original image, which means finding the Z inputs, I guess, that generate that image, right?
Yeah, so yes, this is what you are trying to look for, but of course you are losing information along the way because you have a compressed set of observations that you have only access to.
Right, but it's possible that face. Is it possible that face isn't in the manifold of your system? I mean.
So yeah, so that's what we are going to get to in a few.
Oh, okay, all right. Sorry.
So it's an excellent question. I fully agree.
Yeah.
Okay, so I mean, just to take a step back on the strategy, we are just now going to look for solutions to the inverse problem that are going to involve a trained generative model. So prior to solving the inverse problem, we need to have access to a data set to train our generative models. And then we are going to solve by looking for a latent representation that produces images that are in accordance with the observation. Okay, what can go wrong? So there is this problem of representation error, which I think is exactly your question of what if the image I'm actually trying to reconstruct is not in the range of the generative model? There is a problem of, I mean, related of generalizing out of the training set. So how tied am I to the type of data I fed to the generative model when doing the reconstructions. And I think there is even the much bigger problem of having at all access to a training set. So for the two first type of problem, we can represent, I mean, I can tell you a bit more, just show you indeed that there can be problem. So as you were saying, so I can try to find directly without losing any information, takes a given image XD and try to find whether or not there is an image within the range of the generative model that is going to correspond to this image. And the answer is that, for example, with this DCGAN, well, no, there is a substantial representation error. So here you have the original images, whereas here you have the images that are reconstructed by the GAN, and you can see that there is, even though the GAN had all the information to reconstruct the images, it was not able to do so perfectly. So there is a substantial representation error to those deep generative models.
This is sort of what you're doing right now. So.
Sorry, is there a question?
Sorry. No.
And then for the question of generalizing out of sample, so the training data that they look actually, I mean, for example, the data set that was used here is called Celeb A. So it's a data set of images of celebrities that are young and smiling. Now, if we are trying to reconstruct images from still faces, but that are maybe a bit out of this range, you can see that it's doing actually quite poorly. So you have here the true images. So those are the authors of the paper, by the way. And this is the convolutional outputs. And you can see that if you are trying to reconstruct an image with someone with a beard or sometimes somebody with a turban, then it's too far from what the generative model was trained on in order for the generative model to actually succeed in the reconstruction. So interestingly here, there is another type of generative models that is partially answering those two problems, which are normalizing flows. So normalizing flows are deep generative models that work in the same fashion as the deep generative model, in the sense that they have a latent distribution that is propagated in order to create signals. But they are backjective, so they are only involving invertible transformations, such that from an image we can actually compute the invert and the latent representation that corresponds to it. And effectively, this means that they have the same dimension in the input and in the output. So they can be trained with maximum likelihood. And if we go back to this compressive sensing example, we will see that they have zero representation error, meaning that they are going to be able to perfectly reconstruct on those examples that are not too far from the training set. And they can even generalize well out of the training set. So here you have images even of Shrek that are well reconstructed under this compressive sensing problem, thanks to normalizing flows. So of course, this is not at all intuitive, because here there is not this idea of the low dimensional manifold that is being captured by the architecture of the network. And it's ongoing research to understand what is working, I mean, how things are working here. And I'm happy to discuss with anybody who is interested. And if we go back to this general strategy slide with what can go wrong, so normalizing flows are part of the answer for those two first problems. But I think what is much more salient is actually the very problem of even having access to a training set. And what I'm going to say next is for now restricted to the case of images. But it turns out that there can be untrained neural network priors that are still good representations of the data. And so if I just remind you what was the workflow for the trained models, we had a data set that was used to train the generative models. And then we were looking for the latent representation that was optimal. With the dataset free strategy that was proposed in this paper, Deep Image Prior, and a subsequent important work is the Deep Decoder, one will draw a fixed latent representation. And this is not going to be changed anymore for the whole process of reconstruction. And then adjust the parameters of deep neural networks to the single observations that we are trying to make the reconstruction from. So find the parameters of the neural network theta star. And then the reconstructed image will be just the transformation of the fixed random latent representation by this neural networks that has been adjusted just to the one observations. And the intuition is that this works because neural networks architecture, and in particular convolutions, are biasing the reconstruction to natural images. And of course, this is something that looks very promising because you don't even need to have access to a training set in order to be able to make the reconstruction. And I can tell you rapidly about two examples of this application of those untrained image priors. The first example is for coherent diffraction imaging, and it's based actually on a paper we recently submitted with collaborators at CCM. And CDI is an imaging technique that enables to make images at nanoscales using typically X-rays. And so there is a beam of X-rays that is going through a specimen, and then the diffraction pattern is collected on the CCD. And here we are going to focus on the holographic setting, where we add a known reference in the beam. And this is to help the reconstruction. And one of the things that is also making this reconstruction difficult is the fact that we have a beam stop mask that is going to zero out, or mask what's the highest intensities pixels in the CCD in order to protect it, because those are several orders of magnitudes larger than the intensity of the rest. And so in this example, the noiseless forward model is that the intensity that one is going to collect on the CCD is equal to, so the Fourier transform of both the specimen and the reference that is masked by the beam stop, and then taking the magnitude of this Fourier transform. So that's the noiseless case. But it gets even more tricky because in practice, one often needs to be in the low photon regime, so only have a very low intensity beam that will go through the specimen. And this means that these measurements will be highly corrupted by a Poisson shot noise that is modeling what is going on in the reception of the photons on the pixels. And there will be a parameter n sub p, that is the number of photons per pixel that is controlling this level of noise. And okay, so based on what I just said about how we can use untrained priors to do the reconstruction, the proposed strategy that we have is to incorporate the forward model in the objective. So the forward model are those two equations I was just showing. And this means really taking into account the fact that we have a Poisson distribution for the noise and not using the squared loss that I've been using without even really thinking about it since the beginning of the tutorial. And then, so do the reconstruction with the untrained prior, meaning that writing the math about how we are going to minimize the error with the forward model, I mean, we would get this outcome. But importantly, we have replaced the image by G theta of that, and we are going to optimize the parameters of the untrained prior. And then reconstruct the image by just projecting on the data by passing the latent distribution to the generator. And this optimization can be done using just PyTorch, so a deep learning package. And if ever somebody is interested in doing Fourier phase retrieval onto the images, actually for this publication, we have a coded up package that we will soon release and that we are happy to share with everybody anybody at Flatiron that would be interested. And okay, implementing this strategy, we were able to compare it to benchmark algorithms for different levels of noise. And here, the higher number of photons mean the lower number of level of noise. And we can see that if we are comparing to benchmark algorithms, either doing the and direct optimization, but all the more so if we are including an untrained prior, we are really managing to reconstruct much better this image of virus. And if we have very, very drastic level of noises, we are still able to distinguish a bit the outline and the contrast of the image, which is lost by the other algorithms. And we were also able to look at the impact of the area under the beep stop, so the information that we are losing at the center of the diffraction pattern, so the low frequencies. And again, against benchmark algorithms, as we are increasing the number, the area that is lost under the beam stop, using this strategy is really making a difference, which, and all the more so if we increase the noise, and which really inside the fact that these type of untrained priors could be really practical tools in experimental conditions with all of the challenges that goes with it. But of course, this was for simulated data. Now it's nice that you have, that there is another example that is on the MRI. So what's nice about MRI is that actually we can look at the accelerated MRI problem, in which case we are applying those idea of compressed sensing to take fewer measurements in order to do the reconstructions. And this means that we can have some ground truths, which is the case where we would have taken all of the information by taking the time of making all of the measurements and not downsampling it. And okay, and in this paper, very recent, they were able to show that untrained priors were behaving similarly than a supervised method for solving inverse problems, and better than classical regularization methods such as the total variation. So that was all that I wanted to mention today. And if I just summarize it in a few words, we've talked about classical methods that rely on sparsity, up to an application that goes to the acquisition itself of the signal in a compressed fashion. And then we discussed generative models and how we can even use them if we don't have access to a data set. And there are more ways to incorporate machine learning in inverse problems. And if you are interested, you should check this review, Deep Learning Techniques for Inverse Problems in Imaging, where, for example, you can see that depending on the information you have about the forward model or the training data that is available, you have a lot of different things that one can do. And with this, I'd like to thank you for your attention.